Capacitors have a voltage across their terminals as long as there's some charge on the capacitor. We can express that as an equation. Resistors have a voltage across their terminals as long as there's current flowing through the resistor. And inductors have a voltage across their terminals as long as there's a rate of change of current. The voltage is equal to negative L di dt. There's another equation for the capacitor that says capacitance is equal to epsilon naught times A over D. There's another equation for resistors that says resistance is equal to rho times L over A. So what's the equation for inductors that tell us what's the value of the inductance based on the geometry? For example, if our inductor is a solenoid with length L and cross-sectional area A, how can we calculate the inductance? So I remind you how we got this equation from this equation. If we rearrange this first equation, it tells us the very definition of capacitance is a ratio of charge over voltage. So let's draw a Gaussian surface for the top plate of our capacitor. I'll make my Gaussian surface something like a soup can. So electric field lines are very nearly uniform. Near the edges of the plates they start to curve, but through the two end caps of my soup can the electric field would be uniform. So let's state Gauss's law. The integral of E dot dA is equal to the amount of charge inside the Gaussian surface divided by epsilon naught. Here, if the electric field is uniform, I can take it out of the integral. The dot product is easy to calculate if the electric field and area vectors point in the same direction. And so we find there's just flux through that end cap and that end cap. So the whole left side of the equation becomes E times 2A. And then the amount of charge that lies inside is just the amount of charge in that portion of the total plate. So we could state that if the plate has a uniform charge density, then Q in would just be that charge density multiplied by the area. So we get E times 2A is equal to sigma A over epsilon naught, and now area cancels out, and we have electric field is sigma over 2 epsilon naught. But that was just the electric field due to the top plate. Of course, there's two plates, so the field is doubled. So the net electric field is equal to sigma over epsilon naught. And then sigma, since it's uniform, not only is there a sigma for the part of the plate that was captured by our Gaussian surface, but it would be the same density of charge across the whole plate. So we can say sigma is equal to the total charge Q over the total area. So we can replace this and say our electric field is equal to Q over epsilon naught times A. And then voltage is equal to the integral of E dot ds. So if the distance between the plates is d and electric field is uniform, we can take it out of the integral. Oops. So we have E times the integral of ds as we go from 0 to d. And so we just have V is equal to, well, E is Q over epsilon naught A, and the integral of ds from 0 to d is just d. So if capacitance, by definition, is equal to charge over voltage, then it's Q over QD over epsilon naught A. The Q cancels out, and lo and behold, we had it right. Capacitance is epsilon naught times A over D. So is there a similar approach for finding the inductance of a solenoid? Well, it turns out, yes, there is. And that's the topic of this video lesson. Before we find the inductance of a solenoid, let's try to find the inductance of a single loop of wire, maybe something like a winding that only goes around once instead of several times, or maybe a couple of loops. There's a practical example of having inductance of just one or two loops. You might have noticed on some of your USB cables that there's this cylinder near the end of the cable. They sometimes refer to that as a choke, sometimes called a ferrite choke because the material that's inside of this cylinder is iron. So ultimately this USB is probably going to be plugged in to some electrical device that has an integrated circuit inside. And if there's a sudden spike in the current that flows in this cable, that could damage parts of the integrated circuit. One, you could have rapid thermal expansion of some of the fine wiring that exists in the integrated circuit if there's a large value of di dt, right? There's not just a value of I, but what if you get a surge in the current so that there's a value of di dt? Then that rapid changing current can cause thermal expansions on these very delicate wirings, which would be no good. It can also, according to our equation for voltage, if di dt is really large, there can be a big back EMF, and that can create arcing across small components of the integrated circuit. So needless to say, we want to try to eliminate any values of di dt. So what you want is a large inductance in the wire before it gets plugged into your integrated circuit. So if you ever take apart one of these ferrite chokes, you'll see that the wire doesn't just continue through, it gets looped around and then carries on to the USB port, and that loop is inside of the ferrite choke. In fact, they have clip-on versions of these where it's up to you to wind the wire around yourself after you've clipped it onto the wire. So if we rearrange this equation, we could put it in a triangular form and say there's a relationship that can be solved anyway. In other words, instead of having the equation expressed for V, we could have the equation expressed for L, and we get L is equal to V over di dt, or we could say di dt is equal to V over L. We could put that all together by putting it in triangular form and say say V is equal to L di dt. But we also know that the behavior of this voltage is in accordance with Lenz's law and Faraday's law. In other words, the voltage is negative L di dt, but we should also be able to say, according to Faraday's law, that the voltage is negative N d phi dt. And so if we set these two equal to each other, if negative L di dt is equal to negative N d phi dt, then we can cancel out the negative sign. We can cancel out the dt. We can integrate both sides of the equation, and we get L times I is equal to N times phi. So perhaps that's another way that we can figure out inductance. L is equal to N phi over I. In fact, that's how we'll go about it. So in the same way that we had a starting equation for figuring out capacitance of different shapes, capacitance is by definition a ratio of charge over voltage. We'll say inductance by definition is equal to N flux divided by current. So back to our single loop, which is very much like a ferrite choke. How would we apply this equation? Well, phi is equal to the integral of b dA. So first thing, what if somebody were to look in this direction on the loop? Then from a top view, as the current flows this way and then spirals around that loop, This person might see it as just a current flowing around in a circle. And so we can derive an equation for the strength of the magnetic field inside of that loop. Actually, we'll start with the law of Biot Savart. A little bit of magnetism just from a small segment of that loop that we call ds. That little bit of magnetism is equal to mu naught over 4 pi times I ds cross r hat over r squared. That's the law of Biot Savart. So if I want to find the total magnetic field inside of the loop, then I need to add up all the contributions from every little segment ds. So when I substitute for dB and take the mu naught 4 pi and I, since they're constants, out of the integral, I'm left with mu naught over 4 pi times the integral of ds cross r hat over r squared. Although in this case, the vector r hat and the vector ds are always perpendicular to one another, so we can ignore the cross r hat. And for every ds, the value of r, the distance to the center of the circle, is the same. In fact, that's capital R, the radius of the circle itself. So we have b equals mu naught I over 4 pi. I replace lowercase r squared with capital R squared, and I take it out of the integral. And now I'm just left with the integral of ds. But of course, that's just going to give us the circumference of the circle. So we get b equals mu naught I times 2 pi r over 4 pi r squared. Pi cancels out, one of the r's cancels, and 2 over 4 can be reduced. So we find the magnetic field is equal to mu naught I divided by 2r. So from here, it seems like it shouldn't be too difficult to find the inductance of this loop of wire. All we need to do is say, well, since it's a single loop, n equals 1. If it was like this one here, it looks like we've got 1, 2. Okay, so then we'd have a case where n equals 2. In any case, the n is easy to account for. The I is easy to account for. I is just the amount of current that's flowing through our loop. So phi, how do we get this? Well, you might make the mistake of saying phi is just b times a. We just found b. It's mu naught I over 2r. And I know the area of a circle, area is pi r squared. You see the problem with this? This expression for magnetic field, maybe we should put b naught. That's only the strength of the field right at the very center of the loop. In other words, right at that point. But the magnetic field at this point, or this point, or this point is not of the same value. And so we really can't just say phi is b times a. We have to say flux is the integral of b dot dA. And so this actually ends up being very challenging to come up with an expression for phi. So in general, we'd like to be able to say that L equals n phi over I as a way to derive an inductor maker's equation. But in the case of a single loop of wire, it's not so easy. However, the title of this is the inductance of a solenoid. We want to find what's the inductance of several tightly packed loops. And that ends up being very doable when we use an equation of this form. So let's start with a picture of an inductor as opposed to a single loop. And we'll try to derive an equation for the inductance based on the geometries. So here are some of the geometries involved. There's a length overall for our inductor. There's a cross-sectional area A. And there's also, well, you decide how you'd like to picture this, lowercase n or capital N. Capital N is the number of loops or the number of windings, whichever way you like to say it. I'll say number of loops. Lowercase n is the density of loops, or in other words, it's the number of loops divided by the overall length. In any case, those are the geometries. Cross-sectional area and something that has to do with how tightly wound the wires are. L, by definition, is n phi over I. So the real trick is coming up with an expression for the flux. Well, flux is equal to the integral of b dA. In our last problem, we weren't able to finish our calculation because it was difficult to compute the integral of b dA. However, if the magnetic field was constant at all points in the loop, so if the magnetic field there and there and there and there was all of the same value, then we'd take the b out of the integral sign and we could just express flux as being a constant value of b multiplied by some area. Well, you know that's the case for a solenoid. If the current flows in this direction and wraps around behind and then goes around in these loops, you can use the right-hand rule and convince yourself that there's magnetic field lines pointing in this direction, and that magnetic field, as long as we stick to regions near the center of the solenoid, is very nearly uniform across the whole or throughout the whole cross-sectional area of the solenoid. So we can simplify our expression for flux as just a product of B and A. So one step at a time. In the end, we're going to try to use the equation L equals n phi over I, but phi is B A, and we can get B from Ampere's law. So to remind you, Ampere's law, it's the one that says the loop integral of the vector dot product B dot ds is equal to mu naught times I enclosed by some Amperian loop. This is similar in a way to Gauss's law for electricity. So we need to picture some sort of Amperian loop and see how much current is enclosed. So I'll make my loop a rectangle. And as we saw in our previous picture here, the magnetic field at regions inside of the solenoid are much greater than they are outside. In fact, these magnetic field lines go very far away before they wrap around on themselves, and this magnetic field line even farther so. So the magnetic field at points just outside of the solenoid are practically zero compared with the magnetic field at points inside of the solenoid. So as far as there being a dot product between B and ds, there really isn't any on this segment of my loop. And this is not a wire loop or an actual loop of any physical material. This is just an imagined loop. So the magnetic field points, how do we draw it? In this direction. And so because we're taking a dot product, if the magnetic field points to the right, but ds points, choose a different color, ds points downward on this portion of my imagined loop, then there's no dot product between B and ds there either. And then my ds points upward on this part of the loop. So what I'm really saying is there's four sides to my imagined loop: A, B, C, and D. However, there's no product of B and ds along B or D because the magnetic field and ds are perpendicular to one another. And there's also very little product of magnetic field and ds along part C of my imagined loop, because the magnetic field is practically zero along that path. So I'm really only left with a product of B dot ds along part A of my Amperian loop. And so I can replace integral of B dot ds simply with B times L, if I say the length of my Amperian loop is L. Now maybe I'll call that L prime so as not to confuse it with the L I stated earlier as being the total length of the whole solenoid. So the integral of B dot ds is B times L prime, and that should be equal to mu naught times the amount of current enclosed by that imagined loop. So B times L prime is mu naught. Now, if we say the current flowing in this wire is capital I, then on this first winding, that current doesn't pass through my Amperian loop. And on the second winding, it doesn't pass through. But by the time I get to this loop of wire right here, now the current is just starting to go into my Amperian loop. In other words, my Amperian loop is now enclosing that current. And then it wraps around and passes back through it again and again and again. So there's some number of windings that I'll call capital N. And if I multiply the number of windings, capital N, let's see, that's 1, 2, 3. Well, I'm not going to take the time to count them all, but there is some finite number of times that the current passes through my Amperian loop. So if I multiply that number of windings times the current I, that gives me how much current is enclosed. So B is equal to mu naught N over L prime times I. I could replace N over L prime with lowercase n. So B is equal to mu naught times the density of windings times the current. So there we have it, an expression for magnetic field. So remember what we're trying to solve for, the inductance of the solenoid. And we said by definition it should equal N phi divided by I, which in turn is N BA. I can replace phi with BA as long as magnetic field is uniform, and thank goodness in a solenoid the magnetic field is very nearly uniform. So we get NBA over I, and now I have something I can substitute in place of B. So we get L is equal to mu naught N I times capital N times A, all divided by I. So notice the current cancels out, and of course it should. Whether the current flows in my solenoid or not doesn't change the fact that it has an inductance based on its geometry. So the inductance of my solenoid is equal to mu naught lowercase n capital N times A, but then again lowercase n is capital N over L. So we can say the inductance is equal to mu naught N squared A over L. And there you have it, the inductance of a solenoid.